When LIGO announced that they had detected gravitational waves earlier this year, we were inundated with artistic renderings of gravitational waves. Fantastic images like this one, produced by the LIGO team themselves, that help us to visualize this weird phenomenon. But in all the graphics that I've seen, there's a kind of disconnect between the objects and the waves that they produce. There's no way to see how one causes the other. And I think we can fix that with an actual physical demonstration of gravitational waves. My plan is to take a classic demonstration of the warping of space-time and just push it a bit further. See if I can get it to demonstrate something it's never demonstrated before. I'll run through the standard demonstration first. So here we've got a sheet of Lycra. Imagine that this is our universe, or at least a two-dimensional version of our universe. And just like the real universe, when you introduce a massive object, it warps space-time. And just like in the real universe, when you warp space-time, the paths of other objects bend around like that. So there you go, we have maybe a moon orbiting around a planet. That's pretty cool. Actually, I'm quite pleased with this because this ball here looks a lot like Mars. And the reason it looks like Mars is because it's rusty. It's covered in iron oxide. And Mars is that reddish brown color for the same reason. It's covered in iron oxide. But anyway, you can also simulate a massive object in this universe by pressing your finger into it like this. So there you go, I'm warping space just in the same way that a massive object would, and if I want to simulate a more massive object, I just push harder. That will become important later. This analogy for the real universe is okay. It's not perfect. In fact, I touch on some of the imperfections in the previous video about LIGO that I made with my wife, where we discuss gravitational waves. But this universe does have something in common with the actual universe that makes it really good for demonstrating gravitational waves, and that's a speed limit. So our universe has a speed limit of about 300 million meters per second. Nothing can travel faster than that. Most things travel slower than that. Some things travel at the speed limit. So light, for example, travels at the speed limit of the universe, which is why we call the speed limit of the universe the speed of light. And so you probably know this, the sun is very far away, so it takes light about 8 minutes to reach us, meaning that if the sun were to suddenly go out, we wouldn't be aware of it for another 8 minutes. And it's the same with gravity. Gravity travels at the speed of light, so if the sun were to suddenly disappear, we wouldn't be aware of it. We wouldn't feel the gravitational effect of that for another 8 minutes. And I can demonstrate that in this universe here. So if I suddenly introduce a massive object into this universe. Let's watch that in slow motion. So you can see this region of space isn't yet aware of this new massive object that's been introduced into the universe, because that warping of space-time is traveling outwards from the source at the speed of light. And there you go, only now does it feel the effects of that massive object. Of course, in the real universe, objects don't suddenly disappear or appear, but they do move. So, you know, if I have a massive object here and I move it over there, then objects in the distance over there won't feel that change in the warping of space-time until it's propagated over that distance. And this is how we can demonstrate gravitational waves. So what we want is two black holes orbiting each other. This is what LIGO detected. So I can have maybe my two fingers pressing into the fabric and I can orbit them around each other. I actually get a little bit stuck because I can't pass my arms through each other. So I've built something. I've built this device here. So I can spin this around in my universe. And you'll notice we're not seeing any gravitational waves. That's because I'm not spinning this thing fast enough. At the point that LIGO was able to detect gravitational waves from those orbiting black holes were traveling close to the speed of light. So I need to spin this thing close to the speed of light. Fortunately for me, not the speed of light of the universe, but the speed of light of this universe. And I can calculate the speed of light of this universe. If I look at this slow motion footage here, I can eyeball the distance. So I can calculate that it takes about 32 frames of footage to travel about 20 centimeters, and we're looking at 1,200 frames per second. So the speed limit in this universe, or the speed of light in this universe, if you like, is about 8 meters per second. So I need my black holes to be moving at about 8 meters per second. So how many turns is that per second? Well, the radius of the orbit is 0.07 meters, meaning the total circumference of the orbit is about 0.44 meters. So I divide 8 meters by 0.44. That gives me about 18 turns per second. I need to spin this 18 times every second, which I'm not going to be able to do with my fingers, but that's okay because I brought a drill. But that's okay because I brought a drill. Okay, here we go. Well, that looked quite promising. Let's have a look at that in slow motion. How cool is that? An actual physical demonstration of gravitational waves. A couple of extra things. Firstly, one thing that this universe doesn't have in common with the actual universe is that it has an edge. And so far as we know, the actual universe doesn't have an edge. And if it does, then it's so far away that it isn't interesting in terms of this discussion here. But when you have an edge like that, in physics, it's called a boundary condition. And if the boundary conditions are right, waves get reflected. And you can see that in this video here. You can see the waves being reflected. Einstein's equations of gravity allow for all sorts of things that we don't observe in the universe, like wormholes, for example. They're not explicitly disallowed by Einstein's equations of gravity, so maybe we'll find them one day. And I wonder if boundary conditions are allowed in Einstein's equations of gravity as well. I don't actually know, so if you've got any thoughts on that, please let me know. The other thing I wanted to talk about was how I captured the slow motion footage of the gravitational waves, because I didn't use a slow motion camera. Instead, I utilized the stroboscopic effect. And the way the stroboscopic effect works is if you've got something that repeats again and again and again, then you line up the frame rate of your camera with the speed of repetition of the thing you're trying to film. So because the gravitational waves were repeating, it was, you know, the same thing again and again and again, I was able to use this stroboscopic effect. So imagine this, imagine you've got this thing and you set your camera to 1 frame per second, and you also rotate this thing once per second. So it spins all the way around and you take a frame. It spins all the way around again, you take another frame. You spin it around again, you take another frame there, you take another frame again there, and so on. You keep going every time. So if you play all those frames together, it just looks like that. Frame 1, frame 2, frame 3, frame 4, frame 5. It looks like it's stationary. So if you then speed the thing up, so it's actually going slightly faster than 1 turn per second, then you take a frame, it spins around, and then you take another frame there, and then you take another frame there, and then you take another frame there. So when you go through the frames now, it's like there, 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 there. So the thing is slowly moving around. So my camera was running at 25 frames per second. So in the UK, you have a choice of 25 or 50, whereas in America, it's 30 or 60. I'm not going to get into why, because people have already made great videos. In fact, Tom Scott has made a great video, link here, about why there's a difference in the two countries. But suffice to say, I needed to spin this thing at about 18, so either faster or slower than the frame rate of the camera, but I also needed to spin it close to the speed of light in the universe. So the speed of light in the universe was 18 I need to spin it 18 times per second to match the speed of light, whereas I needed 25 frames per second for the camera. So I actually had to speed up the speed of light in the universe to capture those frames. So after I did that bit about how fast I had to spin it, I then tightened the fabric on the frame to speed up the speed of light in my universe to get it to the speed I needed it to be. Anyway, I hope you enjoyed this video. If you did, please hit subscribe, and I will see you next time.